Welcome to the second lecture in an introduction to real analysis. The topics that we will explore in this lecture include techniques of proof and an introduction to set theory. Okay, so we'll start with one of the exercises from the previous lecture. We will show that the implication P implies Q is logically equivalent to its contrapositive, not Q implies not P. And so we'll build a truth table. Recall that the implication P implies Q is false precisely when P is true and Q is false. In all other cases, it is true. Now, the contrapositive, not Q, implies not P, is itself an implication. So we need the case where not Q is true, and so that is a case where Q is false, and not P is false, which is the case that P is true. And so that is this case, and in this case, this implication is false and is true in all other cases. So notice that the truth table for the implication and its contrapositive are identical, or we can look at the biconditional connecting them, and since the values are the same in all cases, the biconditional is always true, and so this is a tautology. And so we have demonstrated that the implication P implies Q is logically equivalent to its contrapositive, not Q implies not P. So next, let's look at the converse of the implication P implies Q, which is Q implies P, and compare that to the inverse of this implication, which is not P implies not Q. Again, we'll build a truth table. So the implication Q implies P is false precisely when Q is true and P is false. In all other cases, it is true. So in the implication not P implies not Q, we need the case where not P is true, and so this is a case where P is false, and not Q is false, which is a case where Q is true, which is this case. And in this case, this implication is false, and in all other cases, it is true. So again, we see that the converse and the inverse have the same truth table. And since these two statements have the same values, truth values, in all cases, the biconditional connecting them is always true. And so again, we have a tautology. And so we have demonstrated that the converse, Q implies P, is logically equivalent to the inverse, not P implies not Q. So we can use these truth tables as a basis for techniques of proof. And so the first that we'll look at is known as a direct proof. Of an implication. So to prove the implication P implies Q directly, We assume that the hypothesis P is true, and then using a series of facts, we demonstrate that the conclusion Q is true. Another technique of proof is based on the logical equivalence of a implication with its contrapositive, and so we call it a proof by contrapositive. So to prove an implication, P implies Q, we prove the logically equivalent statement not Q implies not P. Sometimes the contrapositive is an easier statement to prove. So next, we will show that an implication, P implies Q, is logically equivalent to a statement of the form P and not Q implies a contradiction, which I'll abbreviate contra. So let's build a truth table. As we know, the implication P implies Q is false when P is true and Q is false and is true otherwise. So now for this second statement, let's start with the conjunction P and not Q. So P and not Q is true when P is true and not Q is true, or when Q is false. So we have true false, giving us the combination true, and in all other cases, the conjunction is false. Now, a contradiction is a statement that is always false. So now we look at the implication, and this implication is false precisely when the hypothesis is true and the conclusion is false and is true otherwise. So notice that these two statements have identical truth tables, and so if we join them with a biconditional, since the truth values are identical in all cases, the biconditional is true in all cases. So we have a tautology, and we have demonstrated that an implication, P implies Q, is logically equivalent to P and not Q, leading to a contradiction. So next we'll look at the second exercise from the previous lecture. The conjecture was if A is an even integer, then its square is even, And we will prove this conjecture, which is in the form of implication, directly. So let A be even. So we have assumed the hypothesis. So we'll use a series of facts that will allow us to conclude that the square of the integer a is even. So as a is even, a is of the form 2 times m for some integer m. And so the square of a is the square of the quantity 2m, which is 4m squared, which we can write as 2 times the quantity 2m squared, where 2m squared is an integer, and hence a squared is even, as it is in the form 2 times some integer, and therefore if a is an even integer, then its square is even. So next we look at the converse. The converse is the statement, if a squared is even, then the integer a is even. And we will prove the converse using the technique of proof by contradiction. So let a squared be even, and suppose for a contradiction that the integer a is not even, and if it is not even, it is odd. So we have assumed both the hypothesis and the negation of the conclusion, and so we'll now show that this leads to a logical contradiction. So since a is odd, a can be written in the form 2 times m plus 1 for some integer m. And so a squared is the square of the quantity 2m plus 1, which is 4m squared plus 4m plus 1, which we can rewrite as 2 times the quantity 2m squared plus 2m plus 1, where 2m squared plus 2m, which is a sum of the product of two integers, or three integers in the case of the first term, is itself an integer. That is, a squared is odd, which contradicts the hypothesis that a squared is even. So to be clear, we have that a statement P and its uh, negation is always false. That's the logical contradiction. Always false. And therefore, by contradiction, if a squared is even, then the integer a is even. So recall that a biconditional P, if and only if Q is logically equivalent to the conjunction of the implication P implies Q and its converse Q implies P. And so to prove the biconditional P if and only if Q, we prove both the implication P implies Q and Q implies P. So notice that in the previous exercise or previous example, we proved both the implication and its converse, and so we proved that a squared is even if and only if a, the integer a, is even. So next, we'll look at a new truth table. We'll look at the statements P implies R and Q implies R, and compare this with P or Q implies R. Now with three statements, we have 2 to the third or 8 cases. So beginning with the first statement, P implies R is false when P is true and R is false. So that's this case and this case. In every other case, this implication is true. The implication Q implies R is false when Q is true and R is false, which is this case. And this case. In all other cases, This implication is true, so now we look at the conjunction. True and true is true, false and false is false, true and true is true, true and false is, or false and true is false, true and true is true, true and false is false, true and true is true, true and true is true. So now we look at the second statement, P or Q. This statement is false when both P and Q are false. And is true in all other cases. So now the implication, P or Q implies R, is false when P or Q is true and R is false. So we look for those cases. Here's one. Here's another. And another. In all other cases, the implication is true. So notice that in the first statement compared to the second statement, we have identical truth values. And so if we look at the biconditional joining them, that biconditional is true in all cases. And so we do have a tautology. And so we have demonstrated that P implies R and Q implies R is logically equivalent to P or Q implies R.